All right, so in this chapter, we're going to look at different methods of doing diffuse scatter. And we can basically break it down into two major methods or two major groups that each have several methods within that group. The first method would be to do scattering diffuse light over the entire scene, and we'll sort of get into that as we go along here. And that's methods such as radiosity and photon mapping. And then the next concept is to just do diffuse scatter within what's visible in the viewport. And that's done with methods such as quasi-Monte Carlo sampling and irradiance caching or a final gather, etc. All right, so let's start off first with some radiosity. Okay, so before we get started, I want to point out a few things. These are some very simple scenes that we've set up for these first few examples, and that will help us really determine what's going on in terms of our scenes. Also, throughout these DVDs, most of the scenes I have will try to minimize the use of textures, because textures can help hide some artifacts, so they can get lost in there. And we really want to be able to see them to show you where there are problem areas and where there aren't problem areas, since artifacts is such a big part of what we fight with when we're doing global illumination. So in this particular scene, this is for our radiosity solution, and we'll just take you through that real quick. And it's basically just a kind of a hole in the ground which light can come through, and some colored cubes in there. And basically our hole is got a sunlight system built into it, and this actually daylight system. And this daylight system is using specifically IES light and IES sky. What's important to know about this in terms of doing radiosity is that IES skies and that real-world lighting is really your best benefit when you're doing radiosity. So just to give you a heads up on what radiosity is actually measures the radiation off of surfaces. It was used scientifically to measure radiation off surfaces. And in our particular case, it could be radiation of heat, not atomic radiation, obviously. But, well, maybe you could if you wanted to. But on our purposes, we want to look at the radiation of actual light coming off of surfaces and how that energy gets bounced around. So that's basically where radiosity. Okay, so now we're ready to do our radiosity, and I'm going to go into rendering here, and then advanced lighting, and choose radiosity. I'm going to select no to this particular dialog just to make a point. But okay, so what we're doing is our initial quality is set to 85, and that's going to be plenty for this particular example. And then I'm going to go here and I'm going to hit start, and you notice that it went very quickly and it reconstructed a scene and seems to have added all this light in here. But let's do this, and let's actually render this image and see what happens. And you notice this is an extremely bright image, and the reason being that radiosity, since it is tied to all to the radiation off of these points, it actually is way too bright because it is dealing with real-world lighting. So what we need to do is change our exposure of our image. So we go here to exposure controls, and we're going to select logarithmic exposure, and I'm going to select external daylight. I'm going to hit a little preview render. It gives you an idea of what's going to happen, and that's probably just about right. And we're going to go in here. So for the most part, you're probably going to want to make sure you have your exposure set up correctly when you're doing radiosity. So we are getting some global illumination here, but as you can see, it's very little detail. It's just sort of a little brighter here, a little darker here, and that's because we only have samples of light on each vertices. So in order to really get better detail out of this, we're going to have to create more vertices. And how do we do that? Well, radiosity has that sort of built into it. And what we're going to do is we're going to turn on this, just for now, we're going to just enable the straightforward global subdivision level. And I'm going to select, this is tied to real world units, and that's very important to do that, 2 meters of subdivision. And then I'm going to reconstruct this. So I'm going to reset all, and I'm going to go to start. And you notice it takes just slightly longer, but it's actually reconstructed a mesh and added more vertices to our area in order for us to have more samples to collect from. So if we look at this if we tumble through the scene, we'll see that we actually start to have light starting to get baked in. It's obviously not very detailed at all, but it's kind of nice that light is actually baked in to our scene, but it's also added a lot more vertices. Well, not a lot because the scene was very simple, but it has added quite a bit of vertices to our scene, relatively speaking. So if we do a rendering of this, we will notice that basically we're starting to get more detail in here. There's more noise, and we'll get into solutions for that. But we are starting to get more detail in here. Well, let's push this just a little bit further. and go in here and choose our minimum or maximum size to 0.5 meters and do a reset all on it and start again. And notice now that it actually takes slightly longer to calculate our radiosity because there's more vertices for it to sample from, so there's more radiosity to calculate. So as it's going through here, let's just wait, let it finish, and it's done. We can do a render and we will see that we're getting more samples, but we're getting all of this noise in here. So let's look at it obviously in perspective, and we see that actually we are in fact getting more detail out of this, and in fact it's getting a lot better. Still not good enough for what we want, but we will look at some solutions for that. But the first thing I want to talk about is how do you get rid of all of this splotchy noise over here. And there's basically one way to do it. One good way to do it. One would be to turn this up, and unfortunately we'll never get rid of all the noise. But another way to do it is just to do a regather, and that's going to be, and that regather is going to be very similar to the methods that we will use in the future, such as radiance cache and or final gather that's done in Mental Ray. But if we turn up this gather, and we're able to actually get a better solution. So I'm going to hit render, and it's going to take a little bit longer, so I'll give you the render time at the end. But once I hit render here, it'll get started, and I'm going to pause the video and give you the render time at the end. Okay, so the rendering's done, and the regather process is done after the render itself. During the render itself. And so this actually takes a lot longer to actually do the regather. So what we're looking at here is now all of a sudden we have a rendering time of 2 minutes 30 seconds as opposed to just a few seconds to actually do the render. So it is expensive to do the regather, but on larger, more complex scenes it may be okay. So let's turn that off, and I want to talk about how to get better optimal subdivisions out of here. And there's a great solution for this, which is to do an adaptive subdivision. And that concept of doing an adaptive subdivision actually is applicable to other systems as well. So I'm actually going to start with a maximum of 2 meters and a minimum of 0.1 meters. Or actually 0.05 meters. And what I'm going to do by doing that, I'm going to do reset all, and I'm going to hit start, and it's doing an adapt. It goes a lot faster actually than the last one, but gets much more detail out of it. And notice what it does. It actually is adaptive to our geometry and adds more detail in the areas that we're more interested in terms of the sampling. So when you look at this, it becomes just much more optimal in terms of the subdivision of our mesh, and therefore much much better in terms of a solution, because it will utilize less memory and therefore better rendering time. So let's go back to our view here, and we will do a render again, and we will do it. Let's do it again with, let's turn on, make sure our regather is on as well. I'm going to turn that back on. And we're going to do another render and see what that looks like. So I'm going to hit render. And I'll pause the video. And we're back, and we saw that the rendering time's actually gone down a little bit, and it's probably because there's fewer subdivisions in the mesh, and it's able to deal with it better. And we're also getting better detail in this area, like the contact shadows, etc. And this is a fairly good solution. So we're pretty happy with this. And I'm just going to talk briefly about some of the advantages of doing radiosity, and one of them is basically that obviously it bakes the lighting into the mesh automatically, and it's able to kind of dispense the entire energy of the scene, and it's very previewable in the viewport, which is really kind of great to be able to see this in the viewport, what exactly is going on. Big disadvantage is there's tons of artifacts that start to appear into it, and the only way we can kind of get around that is to do some regathering on our entire scene. So okay, now that we understand this, let's sort of look at another method, which is going to be photon mapping. So for this photon mapping, we are actually we're actually going to look at a this very similar setup. So what we're going to do is we have the same kind of scene, and instead of actually using the IES light, we're going to just use a straightforward direct light. And one thing to keep in mind in terms of photon mapping, well, two things to keep in mind in terms of photon mapping. One is that it's very similar conceptually as thinking of shadow maps. So what I've done here is, if you notice, the light is highly focused on the area, because I want what it's basically going to do is going to shoot photons out of this area, and it's going to shoot a limited amount of photons. If that was a larger area, a lot of photons would sort of go to waste in the same way that a shadow map would go to waste. So it's very important to think of how far your light is shooting, etc. So for this particular scene, I just got one direct light. It's going to shoot photons in that direction, and I'm going to look through my camera, and there's several rendering engines that do photon mapping, and I'm going to choose V-Ray for this one because we're going to use it almost throughout the entire video. And I'm going to go into rendering here, and I'm just going to shoot it. I'm going to make sure I'm going to shoot without any particular global illumination at all. And this sort of gives us our straightforward scene with no GI at all. And notice, obviously, that as we would expect, there's no bouncing around. Everything is dark, and the only area we're getting anything is in these light areas here. So we're just going to go into our indirect lighting. We're going to turn that on, and we have several different methods that we can choose. We've chosen photon mapping for both the primary bounces and secondary bounces. And we've also used a default setting for the light source. And if we go to system, we can select the light system. We just have one direct light, and we've done a diffuse subdivision of 150. And what 150 means is basically 150 times 150, which is 22,500 samples or photons that are being shot out of this particular direct light, which is seems like a lot, but it's actually not enough at all. But we'll look at basically what this does. And so let's just go ahead and render this. And you notice it went through a photon map very fast because it can shoot 22,000 photons very quickly. And we're starting to get our GI in here. The next thing you've noticed is that, similar to radiosity, we actually have a bit of an exposure problem. The way we can solve this is to basically go into our mapping inside of V-Ray, and there's an option called color map, and we have the similar type of thing, and we're going to actually choose exponential. And I know that because I've used this before on this particular scene, you're going to want to mess with these dark multipliers and bright multipliers, and I'm going to change my dark multiplier from 1 to 2, and I'm going to render this, and you'll notice that it actually renders it pretty fast, and it'll even out my lighting quite a bit, so my dark areas become brighter and my over bright areas become a little darker. And you also notice that the rendering time is fairly quick at about 17 seconds, and this is including the capturing process, which can chew a bit of processor time as well. So now that we've done that, what we want to do is try to get better solutions out of this. So let's just go ahead and shoot more photons at the scene. And I'm going to go up by from 150 to 900 subdivisions, which is quite a bit more. When I hit render here, you will notice that the building photon map now has taken up a lot more time. It takes up more time, and it also will take up more memory. So be careful when you're using your photon maps. Photon maps can chew up your memory quite a bit. So now that we've done that, we'll notice that we're starting to get better detail in our areas. We're starting to get the concept of contact shadows, and a lot of these larger splotchy areas start to go away into a more finer splotchy areas, and those can come down even more using some other methodologies. And our rendering time has gone from 17 to 33. Another thing I want to talk about, the advantage of photon mapping, is the fact that it can actually shoot a lot of it can actually do a lot of bounces for very little energy. And I've actually gone up here, and I've got 10 bounces of light. And if I ever went to 30, let's go to 30 real quick, and then I'll pause the video, see what happens. Okay. you'll notice it actually rendered almost as fast, actually just a little bit faster, and that's probably because the light is escaping. But extra bounces of light are virtually a free concept in photon mapping, and it really only becomes an advantage when you're doing it for interiors. The other big, the issue that we also have with photon mapping is that it really doesn't take into account skylight, and skylight, especially for exterior lighting, is what's so critical. So photon mapping really only has an advantage when we're looking at interior lighting, and so what we're going to do is we're going to look at some other methods that are more suited for exterior lighting.
Okay, so now we're going to talk about diffuse scatter when it comes to optimizing diffuse scatter for the viewport rather than just doing it for the entire scene. But before we do that, we need to talk about a few key concepts when it comes to these principles. And this actually applies to photon mapping as well. But in either case, let's start talking about these concepts. And first thing we want to talk about is subdivision. So subdivision is pretty straightforward, but it just basically comes down to thinking about the fact that let's take this as a unit area of 1, and that area could be anything, but for the purposes of this, let's just say it is a pixel. If we subdivide that pixel, we would get by 2, then we would get 2, 2, etc. So this would be 2 by 2 would be basically 4 units now inside of 1 pixel. If we do it by 3, then we do 3 by 3, which would be 9 units inside of 1 pixel. If we do it by 4, then we get 4 by 4, which would be 16 pixels inside of this unit. And this principle is kind of actually important for a lot of things. It does apply to anti-aliasing. When we're talking about anti-aliasing, sometimes we'll take a pixel and we'll subdivide it by 4 and basically do 16 samples inside of 1 pixel, which would be a subdivision of 4. Or we can also do it for things such as sampling in terms of hemispheric dome rays, where we would say 4 rays per sample, which basically would say 16 samples, or subdivision of 4 would be 16 samples inside of that. So it actually applies to anything. And whenever you see the concept of subdivision inside of V-Ray or other packages, it generally applies to this main principle. So if something says subdivision of 4, think it means basically 16 units inside of that. All right, now that we understand that, as another key principle we want to think about, and that's the concept of oversampling and undersampling, which is different. And this is usually referred to as rate inside of V-Ray. So for this particular example, let's think of this area here as where it says 0, or each one of these little squares, as 1 pixel. When we're doing 1 pixel, what oversampling usually means is when we subdivide it, basically. And when we oversample by a rate of 1, we subdivide it by 2. So that would be 4 samples inside of there. Now, if we undersample, we're actually going the opposite way. And if we undersample, if we do -1, basically we're saying that 4 pixels fit inside of that area. -2, we're saying that 4 units of -1 fit inside of it, or 16 pixels fit inside of that. So as we go up and as we go down, that is basically what oversampling usually means. Now, this is undersampling and this is oversampling. So what that usually when we're talking about oversampling, we're talking about it when we're talking about doing things such as anti-aliasing, and when we're undersampling, which is key here, is when we're talking about doing samples for diffuse scatter, where we actually do not want to get more than 1 unit, more than 1 pixel sample when we're doing things. So that's something to keep in mind when we're going through this exercise. Just keep the concept of oversampling and undersampling, and the concept of subdivision. All right, so briefly let's talk, this is a different scene than the other scene, and let's briefly talk about the advantages that optimizing diffuse scatter for a viewport as opposed to the entire scene offers, and vice versa. When you're doing it for the entire scene, the advantage you have is that you can actually save that solution, and you can actually go in and continue to render
from different views and be able to get you won't have to redo your GI. When you're doing it for the viewport, the minute you change the view, you have to basically change everything else. And the way this basically works is that it will create samples of diffuse scatter on a per pixel basis, actually on a per sample. So if you're undersampling, it'd be larger areas. If you're oversampling, it'd be little areas. But for now, we'll go through that. The other big advantage that you have is that it'll add a lot more detail because it's really optimized for the view, so you can really focus on getting the detailed global illumination in the areas that you want. So with that being said, let's sort of look at different methods of doing this. So if I go into my rendering, we're going to choose V-Ray for our particular rendering in this example, and I'm actually going to start with my anti-alias set to a fixed rate of 1. And what that basically means is that I have no anti-aliasing. I'm basically 1 pixel is 1 sample of anti-aliasing. And then the next thing I'm going to do is I'm going to go to my indirect illumination. I have that on, and I'm going to, instead of doing the photon mapping, which we showed last time, I'm going to choose Quasi-Monte Carlo for both methods, okay? And what that is if you see here, I'm going to turn my subdivisions to 2, and my secondary bounces to 3. So basically all that's saying is that I am shooting 2 subdivisions, which is 2 times 2, which would be 4 samples per sample of anti-aliasing out there. And what that means is that because I am choosing to do an anti-aliasing of 1, that means for every pixel I'm shooting out 4 rays and gathering light that's going on in that area, or gathering indirect illumination. And I'm doing it through the viewport rather than the light. As you remember, on photon mapping, we're shooting rays from the light and then they were bouncing around all over the place. Here, I'm actually doing kind of the inverse. I'm shooting them from the camera and firing it out there to try to find out how many samples I have. And as I fire, then they bounce around and they try to see if they collect light, etc. So I'm actually doing it via the viewport, which is the key factor to all of this. So now that I've done that, now that we've covered that, let's sort of look at what this does. And this is going to be a very crude representation. This is exactly what we want for this. And I'm going to hit render. And keep in mind that this will actually be slowed down slightly because we are doing some capturing in the background. And let's see what's going on. Probably froze because I'm trying to do too much at the same time here. There we go. And I actually rendered the whole scene here in about 12.7 seconds with a quite noisy solution. Again, I'm only doing 4 samples when I'm actually looking at the rays here, and it's quite noisy. But I'm also getting the jagged effects here. So what if instead of actually let's kill 2 birds with 1 stone and actually increase this. Actually, I don't want to go that high. Let's do 3 subdivisions at a fixed rate. And basically, when you're doing fixed rate, this works quite well when we're doing Quasi-Monte Carlo, probably better than these methods, and that's just due to the nature that the Quasi-Monte Carlo is working. We were actually rendering an image that is 3 times larger than this and then sampling it all down. So let's go through here and actually hit render and see how that affects it. And you'll see that this crude noise is actually going to start going away. It's going to affect our rendering time as it goes through. Let's see. I'll probably hit pause and give you guys the end result. And you see that it actually took a lot longer. It took 1 minute and 19 seconds, but it's still a fairly good rendering time considering that how many samples we've shot out there. And you notice it blurred this area more because there's actually more teeny little samples in this area. So that gives us a pretty good result. Another thing that you're probably wondering is how fast, what kind of rendering engine it is. And just to give you some idea, the computer I'm using is fairly old. It's about 2 years old, and it's got 2 AMD processors that are rendering 2600 AMDs, which are about 2.1 gigahertz each. So this is, this would probably be on a more contemporary machine. This would be a lot faster. But nonetheless, it gives you a good relative speed increase or as we're jumping from one solution to the next. So now let's go in here and let's keep the anti-alias here the same because we probably have enough anti-aliasing going on. And we'll actually increase this to 8. And what we're doing when we increase this to 8, one thing I'm not going to do is I'm not going to actually go in here and actually let's do this. Let's do a solution of 4. I'm not actually going to do the minimum samples. And what this does is it allows some adaptive amount where it will shoot 4 rays where it needs to and only do 2 rays where it needs to. And this gives us some a great deal of optimization. And this is the part of the nature of the quasi Monte Carlo sampling, is finding the best solution and the most optimal method. So let's do that, and we'll hit render again. And as it starts going through here, I will pause you and give you the end solution. And we'll notice that basically our rendering time hasn't gone up that much, and our solution is not that great. So in order to really sort of get the best out of this, we're probably really going to have to push this a lot further. So what I'm going to do is I'm actually going to go up to 16 samples and take my minimum samples up to, let's say, 8. And we're going to go with this and see how that affects our renderings. And we start again, and I will hit pause again. And now we see that we have a much cleaner solution, and our rendering times have gone up by about a factor of 4. So it's about 4 minutes to do this render. But there's some very important things that we need to see, because this is probably as accurate as you can get in terms of your global illumination, at the expense, of course, of rendering time. But notice these contact shadows and how precise they are. The color bleeding is extremely accurate. There's still some noise in here that's going on, but this contact shadow meets that corner almost perfectly, and there's the exact amount of light coming off of here. And this is extremely accurate. You see that color bleeding starts to happen here. And this is kind of the important part of what we want to achieve. We want to be able to achieve this, but not these kind of rendering times. And if you sort of think about what we went through in terms of the radiosity solution, the radiosity solution allowed us to subdivide our mesh, but only optimize it for these areas. So if you take that into account, and you take into account what we were talking about in terms of adaptive, in terms of oversampling and undersampling, basically what we want to do is we don't really care about sampling under a pixel, which is what we were doing in this area. We care only about sampling in this area. But here, we really want to care about actually sampling nice little areas. And that's when we start to look at a different method called irradiance caching, which really is much more adaptive in terms of the amount of samples that it gets. So let's look at that real quick. Okay, so the irradiance cache method, we'll start with the same scene we have just from the last scene. The irradiance cache method in V-Ray is actually very similar. There's lots of different methods out there that use this concept. And it's really basically a regather method. Mental Ray has a great regather method. In fact, in the last system, when I was resampling and when I was doing the radiosity solution, I was resampling to get rid of all that noise. That was basically the same concept, was to do a regather method. But the one that exists inside of V-Ray is quite nice, and I'm going to start with that solution. The first thing I'm going to do is I'm going to get off of doing the sampling, which is the fixed rate. And while this works out to be a pretty good method when we're doing a brute force method, the adaptive subdivision, especially on solutions like this, turns to work really great. And that basically what I'm saying is I'm actually undersampling large areas for my anti-aliaser and oversampling areas which are close to corners or textures, etc. And it's a very good method, especially when we're dealing with very smooth areas such as this. So what I'm going to do now is I'm going to go to my indirect illumination, and when I'm doing an irradiance cache method or a quasi-Monte or a final gather, it only really works for the first bounce. every other subsequent bounce needs to be done through another method. And for that, I'm actually going to stick with the quasi-Monte Carlo method, which is a pretty good way to go. So I have my irradiance cache, and I'm actually going to turn my quasi-Monte Carlo down to 8 again. And that's down to 8 as well, too. So all subsequent bounces, all the first bounce, it's going to bounce, and then after it bounces off, it's going to use the standard quasi-Monte Carlo sampling. So now we start with the irradiance cache. And the irradiance cache is quite an interesting method, way to go. And what the people who wrote VRay, there's a lot of different ways that you can sort of tweak these values. But what they've provided is these great little presets. And the presets allow you to basically say, how accurate you want your solution. That's very low, medium animation, which provides optimal methods for doing animations, and high animation, and very high. So for now, we're not going to go with very low. We're just going to go with low. And when we go with low, it's actually grayed out, but at least you can still see the values. We're actually undersampling by -3 and then to -2. So that's in the same way that you remember that we were doing our irradiance or our radiosity subdivisions. We're going from a 2 meter to a 0.2 meter solution, and that basically is doing the same thing. I'm undersampling by -3 and then as a minimum rate of samples, and my maximum rate is going to be down to a -2 solution. The other big thing to notice is this, and I'm actually going to turn that value down. The default is 50, and I'm going to turn that down to 20, and that's a lot of hemispheric rays. Basically saying 20, that's 20 times 20, which is 400 samples that we're shooting out there for every sample of irradiance cache. So let's shoot this. The other thing I'm going to turn on here is show the calc phase, and I'm going to render this real quick, and we should be able to see the calc phase, and it's gone through there, and you see it's gone through the first sample, and then it's gone through the second sample, and it's actually rendered the whole thing, and it renders it fairly smooth. And they rendered it in 18 seconds. Now notice that all the noise there's pretty much no noise, and it looks almost as good as we had before. There is a key difference. Do you remember how accurate these contact shadows were, and how accurate these were, and how this corner you saw a perfect little thing, a little contact shadow here? We don't see that anymore. And the reason being, let's do a quick render here, and we have this ability to do show samples. So I'm going to do that, and I'm going to hit pause while this goes through. When I turn on show samples, it's quite nice. It actually renders out and shows me where the samples are. So I'm actually seeing every single one of these dots represents a sample of light. And you notice, obviously, that's an area that's much larger than a pixel. And that's quite nice to be able to actually see where it's shooting samples. And you notice that while we're getting a few extra samples in here, and a few extra samples along this edge, we're not really getting them where we need to. And that's probably because we have only not much difference between our minimum and our maximum. And while our minimum samples is able to cover areas that are about this big, which is nice, our maximum is actually not quite small enough to get into little areas here, or not big enough, right? So we need to oversample a little bit more in this area. So I'm actually going to go in here, and I'm going to turn this to medium. I'm going to turn show samples off, and we're going to hit render again. And then as I unpause it, you saw that the rendering time was 19 seconds, and we start to actually see a few more detail, a little more detail starting to come out in this area. So let's look at this again with the show samples on. So I'm going to go back in here. I'm going to turn show samples. Obviously, I'm just doing this to illustrate. You wouldn't have to practically do this. This is just a great way to illustrate it for the demo purposes. I'm going to hit render again. And we'll see that because we've gone to the medium setting, and we'll go through those settings next, we'll see that we actually have better solutions in here. That's because we've started to undersample a little, or oversample a little bit more in this area. So if we look at this, we've actually gone from -3 to -2 to -3 to -1. So we've actually gotten this to be able to go in here and get more samples. And the way it actually does it in V-Ray, you probably can't see it because of the way that it's capturing. It actually goes through several phases. It'll do a render of samples at -3, do another render at -2, and another render at -1. So the larger differences between this, the more times it'll go through a rendering. But it goes through those quite quickly, as you can see, and it'll do the solution we're looking for. So let's turn show samples off, and let's go to high. And this is actually going down to 1 pixel of sample. And we will look at this solution right now. So let's check out what that does. So now we've gone to high, and our rendering time has gone up to 30 seconds. And you're saying, okay, so it didn't increase that much. But here's the key difference. Look at this. Look at how our contact shadows are actually approaching the quality that we had with our Quasi-Monte Carlo. And we're getting actually able to get the color bleeds the same way. And here as well, it's starting to appear quite nicely. Now, you're thinking, wow, this is about as good as we've seen, but it's actually got some problems. You barely can see it, but there is some, what you would call splotchiness in this area. And we need to be able to, if we wanted this to be to look good, we have to get rid of all of that splotchiness. And the only way we're going to be able to achieve that is to be able to increase our hemispheric subdivisions. And the default, as you remember, was 50. Which is quite high, but you're saying, wow, am I really going to shoot 50 times 50 with 2,500 rays per sample? And the answer is actually no. And the reason it's not is because our our sampler is able to be very adaptive and only shoot 50 subdivisions if it needs to. And then any other time, it's going to go, it's going to be a minimum of 8, but it's substantially less than 50. So it'll be adaptive according to how many samples and how much noise threshold you want out of it. And the other thing it does is it kind of blurs it together by doing this interpolated samples. So these samples says basically, of all those little dots, take the 20th nearest ones and then add them all together to create the solution that we want. So the larger this number, the smoother the solution, but the less accurate this is. And these two values are generally set here, and I find them to be quite good for a majority of the cases, to be precise. But of course, it does vary from scene to scene. Now, your next question is, when does it know to add more samples or to not add more samples? And the whole concept of that is actually, let's go to custom, and she'll give us our values, is these particular numbers right here. And this says basically when it'll add more samples is when distances are between objects are very small. It'll add more samples when normals are the difference between two normals, this normal and this normal at almost 9 degrees. It'll add more samples here as opposed to here. And then the last one is color. When color differences, obviously for color bleeding, are big, it'll add more samples as well. So all of those thresholds control when it adds more samples or less samples. And generally speaking, these are set up quite nicely with these presets, and so it wouldn't really mess with them, but it is give you a good idea of what's going on. So if you look at this, I mean, you do see some noise in this area. So if we take it up to 50 subdivisions, which is our default, and let's check out how what our rendering times are, and if we're able to get rid of most of the noise in this area. So let's hit render. And you can see now that we've done this, this area now, there is no splotchiness anymore at all. And our samples are quite nice and give us probably as good a solution as we want. And that's precisely why that is actually, well, it was on high, which is the same thing. It's exactly why high is a preset. I mean, this is probably as good as you're going to get. And we were able to do it in 31 seconds, which is quite nice. The anti-aliasing on this is pretty good. I would say this is probably as good as it can get in terms of a scene of this nature. And we're able to do it in 31 seconds, which is a lot better than the 4 minutes that we're doing with the Quasi Monte Carlo. So that's really the optimal way to go in terms of this. The other big advantage, obviously, is that it's able to capture sky domes perfectly. That is usually the best way to do sky domes, is to do it within the radiance map method. So now that we've got the understanding of all these different methods of how they work, let's go look at these in more practical everyday situations.